Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very important past paper question on electromagnetic induction from May June 2022, paper 4, variant 2. I said this question is very important because in this lesson, we will discuss one key concept about electromagnetic induction. If you really want to understand electromagnetic induction, then this video is very useful for you. Let's study together. Let's improve together. For our question number 7, part A, we need to state Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction simply tells us that induced EMF is directly proportional to rate of change of magnetic flux linkage. Or simply, you can write down induced EMF in a conductor is directly proportional to rate of change of magnetic flux linkage, means d phi by dt. That's all what you need to write down for Faraday's law of electromagnetic induction. Let me show you how you can write down your answer. This is how you can write down your answer for this question. In your answer, you have to mention induced EMF is directly proportional to rate of. If you write down this, you will get 1 mark, and that is M mark. Means must mark. It has to be in your answer. Means you have to write down this one in your answer, then you will get M mark. If you will not get M mark, you will also not get the next mark. And the next mark is for writing change of magnetic flux linkage, and that is answer mark. If you have got M mark and you have written change of magnetic flux linkage, you will get answer mark. So this is how these 2 marks will be awarded. This question is a typical type of question. You will see this question in many past papers. So you need to understand how to state Faraday's law of electromagnetic induction. For part B, it is given to us 2 coils are wound on an iron bar as shown in figure 7.1. Coil 1 is connected to a potential difference V1 that gives rise to a magnetic field in the iron bar. A voltmeter measures the electromotive force V2 that is induced across coil 2. So here we have coil 2 and here we have voltmeter, and this voltmeter measures electromotive force across this coil. And this one is the iron bar. As you can see, this one is the iron bar. This rectangular shape is representing iron bar. Here we have coil 1, and this coil 1 is connected to potential difference V1. So this is a source of power supply. For this question, it is also given to us figure 7.2 shows the variation with time t of the magnetic flux density in iron bar. As you can see in figure 7.2, it is given to us how magnetic flux density is changing with time in iron bar. But we also need to understand coil 2, this is wound around iron bar. So the rate of change of magnetic flux in iron bar is the same as rate of change of flux in coil 2. In this case, we are talking about ideal case. Here is no magnetic flux linkage. So you have to be clear about this point. For this question on figure 7.3, we need to sketch the variation with time t of V2, means the EMF induced across terminals of coil 2 between time t is equal to 0 and time t is equal to 0.40 seconds. First of all, let's try to understand this one with the help of induced EMF. Induced EMF is equal to negative, or simply you can say minus d phi by dt, means rate of change of magnetic flux linkage. We can also write down this one minus dNBA because magnetic flux linkage is equal to NBA if angle between area normal vector and B is equal to 0. So we can write down NBA because cosine of 0 is equal to 1, and this one is divided by dt. But in this case, number of turns are constant, so we can take this N out of this, and A is also constant because area of coil is constant. So simply we can write down this will be equal to dB by dt. So this is EMF. EMF is equal to this. Now from here we can find out dB by dt. This one is equal to gradient. So we can write down induced EMF is equal to minus NA times the gradient of figure 2 times gradient. And this is negative sign. This is very important. This negative sign is telling us when gradient is positive, EMF is negative. And when gradient is negative, EMF is positive. So this is very important point we need to understand. Now simply we need to look at gradient of this. As you can see, this gradient is positive. I will be be writing M here. M is positive. Gradient is positive. So the EMF has to be negative. In this part, we can say this is part 1. And in the second part of this figure, you can see this is the second part. And this one, we can say this is the third part. In the second part, gradient is negative. So the EMF induced has to be positive. In third part, gradient is positive. So the EMF induced has to be negative. And second thing, we need to compare the gradient. So we need to compare gradient of part 1 with part 2 and with third part as well. So if you look at part A and if you look at part 3, these two, they have the same gradient. So we can say part 1 and third part, they have same gradient. If gradient is same, it means the magnitude of EMF induced also is the same. So we can say same EMF induced in part 1 and in third part. Now we need to compare these two with this one. Let's say this one is 0, so here we have 1. So here we will have minus 1. If you look at this point, this is equal to 0.15 and this one is 0.25. So we can calculate gradient of region 1 means the part 1. So we can say gradient M1. So I will be writing M1 here. So the gradient of this part will be equal to 1 divided by 0.15. So this is 0.15. Let's try to find out gradient of second part now. In order to find gradient of second part, we can write down the coordinates of this point and coordinates of this point. Coordinates of first point are comma 1 and the coordinates of this point are 0.25 comma minus 1. So we can calculate gradient of second part now in this second part. In this case, we have y2 that is equal to minus 1 minus 1 divided by we have x2 that is 0.25 minus we have 0.15. So in this case, we got this is minus 2 divided by 0.10. So we have gradient 1 and we have the second gradient. Now if we divide gradient 2 by gradient 1, we can find out how big is gradient 2 as compared with gradient 1. So simply we can do this one here. We can write down here M2 divided by M1. So in this case, we have M2 that is equal to minus 2 divided by 0.10 multiply with 0.15 divided by 1. Now if we solve this one, we can find out how big is M2 as compared with M1. If we solve this one, we can find the ratio between M2 and M1. In this case, we have 2. So let me solve this one. 2 times 0.15 and this is divided by 0.10. So simply in this case, we will get our final answer that is equal to 3. So this is our final answer. So it means that M2 is 3 times greater than M1. So we have to consider these points now and we can sketch the graph. So let me show you how you can sketch the graph. So this is how you can sketch the graph. In this graph, you can see this gradient as compared with this one. This is 3 times greater than this. And when the gradient of this line is positive, this EMF has to be negative. We have already discussed here. And when gradient is negative, means the gradient of the second part is negative. So EMF has to be positive and this EMF has to be 3 times of this one. So this is how you can see here. This one has 3 small boxes, 1, 2, 3, and this one has 9 small boxes. You can count from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 times of this gradient. And this gradient of this part is positive. So the EMF has to be negative. So this one is negative. And this one has to be equal to this. So they have the same magnitude. So this is how you can scale this one. I hope this part is clear to you. If you have any questions, just leave in the comments. Part C, it is given to us coil 2 in B is now replaced with a copper ring that rests loosely on top of coil 1. The supply to coil 1 is replaced with a cell and a switch, and switch is initially open as shown in figure 7.4. For part C1, it is given to us the switch is now closed. As it is closed, the copper ring is observed to jump upwards, means ring move upwards. We need to explain why this happens. So the first thing you need to understand, as ring go upwards, it means there is force on the ring that is acting upwards. So this is one key concept you need to understand. And this question is very nice question on EM induction. Let's try to understand this one step by step. If you have clear understanding of this question, it means you can answer a lot of questions, or simply I can say almost every question about EM induction. Means a lot of questions you can answer from past papers if you have clear understanding of this part of the question. Let's try to understand this one step by step. State 1. I will be writing here state 1. When switch is open, we can simply start when switch is open. Magnetic flux here in this ring is 0. So we can say in that case, magnetic flux in the ring is equal to 0. So simply we can say magnetic flux in the ring is equal to 0. So we can say magnetic flux in ring is equal to 0. The second stage we can write down as switch is closed. We can say as switch closed. As switch closed, magnetic flux in the ring will increase. Magnetic flux in the ring increases. As magnetic flux in the ring increases, according to Faraday's law, there is change in flux and the ring will oppose that change according to Lenz's law. As external magnetic field means the external magnetic flux is increasing, so the ring will produce its own magnetic field to oppose that increase in magnetic flux. So simply we can write down the third stage. As magnetic flux changes, change of magnetic flux will cause induced EMF in the ring. Changing magnetic flux causes induced EMF in ring. Changing magnetic flux causes induced EMF. And induced EMF in the ring, this will cause induced current. So that will cause induced current in the ring. So first of all, EMF will be induced. Then this ring is a complete circle. So there will be induced current in the ring. And this induced current will flow in such a way that it will oppose the change in magnetic flux according to Lenz's law. So it will oppose the magnetic flux. So how it can oppose? So this is very important point. Now you need to understand, in this case, the external magnetic field, we can say this is external magnetic field. As external magnetic field in this case is increasing, it increases from 0 to some value. So the flux of the ring due to induced current in the ring, we can write down flux due to induced current. So simply we can say flux due to induced current. So we can say I induced. That flux will oppose. That will be in the opposite direction. So you can see current will flow like this in this coil. And now you can use your right hand rule and you can find direction of magnetic field. In this case, magnetic field of this coil has north pole at the bottom and south pole at the top. So we can also simply sketch this one here. So this is magnetic field of the coil. So it has north pole at the bottom and it has south pole at the top. Now in this case, magnetic flux induced due to induced current, this one has to be in the opposite direction. So it will create its own magnetic field that will have south at the bottom and it will have north at the top. So it has south at the bottom. So simply I will redraw here so you can see what is going on. Current flow in this ring, it has its own magnetic field that has south pole at the bottom and it has north pole at the top. Now if you look at these two poles, means magnetic field of the coil and magnetic field induced in the copper ring have the same pole at the same point. So we have south pole here, we have south pole here. So these two same poles, they will repel each other. So it means there will be force on this ring in upward direction. So that's all what you need to understand. So due to interaction between these two magnetic fields, there is a force and that force is acting upwards because this force is repulsive force. So this one is repulsive force. So this is what is happening in this case. Let me show you the answer, how you can write down your answer. In order to write down the answer for this question, you can simply say changing current in coil causes changing magnetic field. Changing current in the coil, because current will increase from 0 to maximum value, so that is changing current. So there will be changing magnetic field. So magnetic field will also increase from 0 to some maximum value. And changing magnetic flux causes induced EMF in the ring. So as we have discussed here, changing magnetic flux causes induced EMF in the ring. And induced EMF in the ring causes current in the ring. Means induced EMF causes induced current in the ring. And induced current has its own magnetic field. And that magnetic field is in opposite direction to external magnetic field, means magnetic field of coil 1. So as we have discussed, this one has north pole at the bottom, this one has south. So if we draw these two magnets together, you can see same poles, they repel each other. So there is a repulsive force, it will be pushed upwards. Field due to induced current in the ring interacts with the coil's field, means these two magnets, they interact with each other, magnetic fields, and cause upward force on the ring. Upwards force on the ring. So that's all what you need to write down for this question. If you write down your answer in this way, you will get 3 marks, means full marks for this part of the question. I hope this is clear to you, and this is the key concept about EM induction. For the second part, we need to suggest with a reason what would be the effect of repeating the procedure in C1 with terminals of the cell reversed. It simply means that everything else is the same. We simply reverse terminals of this cell. Now this side means this terminal is negative and this terminal is positive now. So in this case, current will flow this way when you close this switch. As soon as you will close the switch, magnetic flux in the coil will increase from 0 to maximum. And also magnetic flux in this ring will also increase from 0 to maximum. So as current flow in this coil, this current will produce its own magnetic field. According to electromagnetism, means electricity can produce magnetic field. And that magnetic field, direction of that magnetic field, you can find simply using right hand grip rule. So in this case, you have to use your right hand and you need to curl your finger in direction of current. So the thumb will give you direction of magnetic field, mean it will give you direction of north pole. So in this case, thumb is pointing up, so the magnetic field induced here, that magnetic field will have north pole at the top and south pole at the bottom. Now we need to understand magnetic field in the ring. So current will flow in the ring because ring is a complete circle. EMF will be induced and EMF will cause current in the ring. And that current will produce its own magnetic field. Meaning current will flow in such a way, according to Lenz's law, that it will oppose the change in magnetic flux. So it will produce its own magnetic field, in this case in opposite direction, because in this case external magnetic field is increasing. If external magnetic field is increasing, B induced has to be in opposite direction. So this is the key concept you need to understand. These two fields have to be in opposite direction. So we can use different color and we can draw the magnetic field, or simply we can say in this case magnet induced due to induced current. They have to be in the opposite direction. You can see this magnet, it has N at the top, so this one will have S at the top, mean opposite. Then this one has S at the bottom, so this one will have N at the bottom. So in this case, you can see again they will repel each other because we have same poles here. So these two same poles, they will repel each other, means the like poles they repel. So again in this case, this ring will experience upward force. So upward force means in upward direction. But you also need to understand, even you open the switch, in this case force will be repulsive. But vice versa is true when you open the switch, because magnetic field here will decrease. So there will be attractive force on the ring. So switch open, attractive force. They can ask you next time about this. When you open the switch, what will happen? So there will be attractive force, so the ring will be attracted downward, so there will be attractive force. They can also ask you in the exam, if this switch is on for a long time, it is closed for a long time, is there any force on the ring or not? So we can say closed for a long time. If the switch closed for a long time, then what will happen? So is there any force on the ring or not? No force, because there is no change in magnetic flux, so there will be no force, so the ring will just stay there. So these things you need to understand about this type of questions. I hope this is clear to you. Let me show you the answer. In order to write down the answer for this question, simply you can say both magnetic fields, direction is reverse, so still there is upward force on the ring. And that's all what you need to understand. I hope this question is very clear to you. If you have any questions, you can leave your questions or doubts in comments. That's all for today's video. See you in next video. And next video will be coming very soon. And in next video, we will also discuss questions from May June 2022 paper 4 variant 2.